Hello everyone. In today's video, we are going to continue talking about reactions at a carbonyl group. In the previous video, we have covered addition reactions, nucleophilic additions at a carbonyl group. So in this video, we are going to look at addition-elimination reactions. So what are addition-elimination reactions? Well, for addition-elimination reactions, it's basically the first step, nucleophilic addition, followed by elimination. So in the elimination step, from a previous video, we know that the nucleophile can get kicked out, and the overall reaction will be considered a reversible nucleophilic addition. In today's video, we are going to cover another two cases, which is when either group Z or group Y gets kicked out, so the leaving group gets kicked out, or when the carbonyl oxygen gets kicked out. So addition-elimination reactions or nucleophilic acyl substitutions are just reactions in which both the nucleophilic addition as well as the elimination occur. So quick recap, the tetrahedral intermediate might be stable or it might not be stable. And in a case where it's stable, you can do a workup to protonate this oxygen, so you can get a organic product as your final product of the reaction. Or if it's unstable, then this lone pair can come down and kick out the nucleophile, and you will get back your starting material, your starting electrophile. So that's a reversible nucleophilic addition. And then if it kicks out either O or Z or Y, then it's considered an elimination, and you will have your final product plus a leaving group. And in the previous video, we have also talked about what makes a good leaving group, and be sure to check out that video if you haven't. Okay, let's move on to some specific examples of addition-elimination reactions. So for addition-elimination reactions, it's also known as nucleophilic acyl substitution. And what's necessary for it to occur is good leaving group present in the starting carbonyl compound. So for example, when the starting carbonyl compound are esters or acyl chlorides or acid anhydrides, and you need a good nucleophile, so the nucleophile will remain in your final product instead of getting kicked out. And you also need an unstable tetrahedral intermediate, and you need it to collapse to kick out the leaving group instead of the nucleophile, or else we would just have a reversible addition reaction. So some examples are esterification and transesterification. So that's just replacing the replacing the carboxylic acid with another ester. And you have your ester hydrolysis as well, and it can be both acid catalyzed or base promoted. So this is the esterification that's very commonly done in student labs. So in the first step here, you have your acid catalyst. So it protonates the carbonyl oxygen, therefore making this carbonyl carbon more electrophilic. So the alcohol can attack it very easily. And then you just have to, after that, you will get your tetrahedral intermediate. And here we actually skipped a step. So after that, you deprotonate this carbonyl oxygen, and then you will get this tetrahedral intermediate. So this is actually an unstable intermediate because it has many groups that have lone pairs that can kick other good leaving groups out. So OH minus is not a good leaving group. However, when we protonate it with H plus, it becomes the leaving group becomes water, so it becomes much easier to kick out. So here it can the lone pair can come down to form a double bond, therefore kicking out the water molecule. So that we just have to deprotonate this again, so that will give us our ester products. So in this case, we see that we have actually the H plus actually acted as the catalyst twice. So here, this is the first catalysis, and this is the catalysis for the nucleophilic addition, and this is the catalysis procedure for the elimination reaction. So as we can see that H plus not only promotes the first step, but also the second step as well. So yeah, it can also promote the reverse reactions of each step. So yeah, alcohol is a better nucleophile than water. So you can have alcohol, so the alcohol doesn't get kicked out. So it doesn't want to get protonated and then kicked out, but water will get kicked out instead. So this entire reaction is also catalyzed by H plus from concentrated acid, which because if you have a lot of water present in a reaction mixture, then the water molecule might attack the carbonyl carbon instead, causing the yield of the reaction to be lowered because you have a lot of water present, and then because of that, it might attack your ester product, causing it to be converted back into a carboxylic acid, and you don't want that. So you can't carry out this reaction in plenty of water. So you usually use concentrated acid. And yeah, so the H plus first makes the carbonyl carbon more electrophilic by protonating the carbonyl oxygen, and secondly, it makes the OH minus into a better leading group. So remember, uncharged species are usually better leading groups than than negatively charged species. So this is the forward reaction, and the backward reaction of this esterification will just be acid catalyzed hydrolysis. So that will make your ester collapse back into your carboxylic acid as well as your alcohol. So that's just so this hydrolysis is just if you reverse every step of this conversion. So that will give you your hydrolysis. Yes, then for esterification, you just have to replace this carboxylic acid with another ester. So for example, OMe here, then you do the same thing to get your final ester product. So that's called esterification because you're essentially replacing the substituent at one side from one alcohol to another. Okay, now for base promoted hydrolysis, just now we mentioned that the esterification shown here and acid catalyzed hydrolysis are actually reverse reactions of each other, meaning each of these reactions are reversible. However, for base promoted hydrolysis, this entire process is irreversible. Why is this the case? Well, because first, the base is not a catalyst, it gets consumed overall. So you see, here we start with OH minus, but we do not end with OH minus get kicked out anywhere. So yeah, this entire process consumes the base. Then secondly, we must note that uh, so to explain why the base gets consumed overall, it's because ETO minus prefers to act as a base rather than a nucleophile. What does that mean? That means rather than this ETO minus attacking this electrophilic carbon in the carboxylic acid, and finally after another process, like after this bond pair goes up to become a lone pair, and then it comes down to kick out this OH minus. Remember, we don't have acid here, so you can't kick out H2O, you can only kick out OH minus. But this doesn't happen because ETO minus prefers to act as a base here to extract this proton instead of attacking this carbonyl group. So it prefers to act as a base, and this causes the OH minus to not get kicked out, and so it will become your part of your final product. So you see here you have a O minus here. So it gets consumed overall. So finally, because this ion called the carboxylic ion is very unreactive, recall the reactivity series that I have given and explained in the previous video, because it's all the way down at the right side of the reactivity series, meaning it's reactive to almost all nucleophiles. It does not want to be attacked by, let's say, another nucleophile, be it water or OH minus or ETO minus. It doesn't want to get converted back to your carboxylic acid and then back to your tetrahedral intermediate. It doesn't want to do that. So yeah, so your reaction basically ends here. And after you have removed all the other reactants, you can actually protonate this. You can actually do a workup and protonate this carboxylate ion to give you your organic carboxylic acid, and that would be basically your end of reaction because you have removed all the other reactants before you can do that step. So yeah, so finally you can quench this reaction with a lot of dilute acid, and that will end your reaction. Because after you added a lot of dilute acid, you basically eat up all the leftover HO minus, and you eat up the leftover OET minus as well. So there's nothing that can happen to the carboxylic acid anymore, and you wouldn't have an excess of acid catalyst. You wouldn't have a lot of excess of acid to act as a catalyst as well because you're just using a dilute acid to quench the reaction. So there are still some challenges of addition substitution reactions, even when you use a catalyst. So to solve low yield and slow reaction, you can increase the concentration of a reactant. For example, you just have to use a dilute acid for hydrolysis, but concentrated acid for esterification. So when you're using a dilute acid for hydrolysis, yes, you still have the H plus ions to catalyze your hydrolysis process, but you also have an excess of water that will help act as nucleophiles for the reactions to proceed. So you basically push the position of equilibrium all the way towards the right. So that's to your product sides for you to get back your carboxylic acid and alcohol. But for concentrated acid, you can use that for esterification because you don't have an excess of water. So the H plus will catalyze the reaction, and you wouldn't worry about water competing with your nucleophile to hydrolyze your product back. Yeah, so you use concentrated acid for esterification. Also, you can you can have a product, you can form a product that's really not reactive. And for example, you can just use a base to deprotonate the resulting carboxylic acid after hydrolysis. So because carboxylate ions are much less reactive than carboxylic acid, there's much less chance that it will get tagged and form back and reverse your reaction. So the reaction becomes more irreversible. Or you can use a catalyst. So for example, you can use your Lewis acid catalyst to increase the reactivity of the carbonyl compound. So what happens is that the Lewis acid catalyst basically attaches to a carbonyl oxygen, thereby pulling the electron density further away from the carbonyl carbon, making it more electrophilic and more readily attacked. So when using a Lewis acid, it doesn't have to be H plus. It can be some it can be it can be a metal ion. For example, you can have some derivative of the tin ion, and then because it's a good Lewis acid, it would just pull electron density away from the carbonyl carbon. So yeah, so by using those Lewis acid catalysts that are not H plus, you can further decrease the concentration of water in your reaction mixture, thereby solving the issue of what if the water comes back to attack your final product and getting your reaction to be reversible. By not having water at all, you basically solve that problem. So another challenge is that addition occurs after substitution. So let's take a look at this example here. So here you have an ester, and then when you're using something like this, so remember we covered this in a previous video, This is called a Grignard reagents, and it will basically react with the carbonyl group here, and then it will kind of substitute out this OMe group, and then you will have your ET group. However, because you might have an excess of Grignard reagent, or even if you don't have an excess of, okay, let's talk about the excess case. So if you have an excess of Grignard reagents, because you still have the carbonyl group that's quite reactive, it can it can add to the carbonyl group even more, giving you this as your final product. So if you want this as your final product, then you basically cannot get it because it will react further with the excess Grignard reagent to give you your multiply substitute and addition product instead of this substitution product. Um, Even if this Grignard reagent is not in excess, let's talk about reactivity again. So this is a ketone, and ketones are more reactive than esters because esters have another resonance form. Sorry, have another resonance form that looks like this. And because of that, this carbon is actually less electrophilic than the ketone carbon. And because of that, ketones are actually much more reactive than esters. And because of this, even if you don't have an excess of your Grignard, because your ketone is more reactive, the ketone whenever a ketone is formed, it will just eat up your Grignard reagent. And instead of reacting with one more equivalent of the ester, your ketone will just eat out all the Grignard reagents. So you will kind of have a mixture of unreacted esters as well as the addition product in your final reactant mix in your final product mixture. And because of that, your intended product, which is this middle, the intermediate, isn't formed, and that makes it really troublesome because you want the middle product instead of the reactant or addition product. So how do we solve this issue? Well, we can use alkyl lithium followed by quenching rather than Grignard reagent. So, for example, we can use this ethyl lithium. So, after it has attacked this carbonyl carbon, you will get this tetrahedral intermediate. And because OLI isn't it can't get kicked out because O2 minus is such a terrible leaving group, you can just leave it as that, and then you can add some acid to your reaction mixture, and that will help you protonate both groups. And after that, because you can have more acid to protonate either one of these OH groups, and then the other OH group the lone pair can come down. So for example, this is the OH group that gets protonated. So leaving group becomes H2O, and then it can get kicked out. And then you will have your ketone product. So because ET minus is such a terrible leaving group, it cannot get kicked out. So by using this alkyl lithium plus quenching method, you are basically preventing multi additions, and then that will give you your intended product. So another way is that you can convert your ester into an acyl chloride. So you are going from the bottom of the reactivity series all the way to the top. And because of that, because acyl chlorides are much more reactive than ketones, you can use a nucleophile to attack the acyl chloride, a nucleophile that wouldn't react further with ketones. So that will solve this problem of multi-addition. So what is one nucleophile that will react acyl chloride and not the ketone product? Well, the reagent is called Gilman's reagent. So that's basically a weaker nucleophile that react at a high rate with your acyl chloride, but isn't really reactive with your ketone product. So that's your Et2Culi. So know that this is just one of the many examples of reagents that can be used. So just bear in mind when you see um, the copper lithium this motif, because it's usually a Gilman reagent and it will react with your acyl chloride to give you your ketone. Okay, moving on, we will be talking about what if the carbonyl oxygen gets lost instead. So instead of Y, X, or Z, the carbonyl oxygen gets kicked out. Of course, it gets kicked out, it gets converted to a better leaving group before getting kicked out. For example, it might be converted to H2O or another better leaving group, and then gets kicked out because you can't kick out a O2 minus. It's too bad of a leaving group. So addition and elimination, O gets kicked out. Loss of carbonyl oxygen is when the O minus in the tetrahedral intermediate gets protonated and H2O gets kicked out. So it happens in acidic conditions only, because if you have a basic condition, the O minus will just stay as an O minus and you can't kick it out. So you also need the presence of a lone pair on another substituent to really kick the leaving group out. This not only applies to the loss of carbonyl oxygen, but everything else we have covered as well. But in those cases, the lone pair can just come from oxygen. But in our case, we need another powerful group that has a lone pair. It has a powerful lone pair to kick the leaving group H2O out. So some examples of loss of carbonyl oxygen reactions are acetal formation, imine formation, enamine formation, and it can be used to prepare alkenes using using a Wittig reaction. So yeah, when you see loss of carbonyl oxygen, sometimes it's used to prepare alkenes with the Wittig reaction. So for the acetal formation, we can recall the hemiacetal formation. So the hemiacetal formation is basically from here to here. So that's the hemiacetal formation. So this is our hemiacetal. And in acidic conditions, this reaction can go on further. So this OH group can be protonated, giving you your good leaving group H2O. And notice that this OH group came from your carbonyl oxygen. So when this H2O gets kicked out, your carbonyl oxygen is basically lost. So after that, your lone pair on the OR group can actually come down to kick out the H2O, giving you another reactive carbonyl compound, because here we see a positive charge on oxygen. It's a formal charge. So you know that this carbon is really electrophilic, even more electrophilic than the starting material. So yes, the reaction will carry on further, and you will have another alcohol unit attack this electrophilic carbonyl carbon, and then after you form your tetrahedral intermediate, you just have to get rid of this oxygen, and that will give you your acetal. So this is called acetal. So the first step here, when you form this, we have covered this in the previous video. You can use either acidic or basic condition. But once you have formed this intermediate, you must use the acidic condition to proceed. So if you are using the basic condition to do the first conversion here, you must change the condition to acidic in order for you to get your acetal. If you're using your basic condition, then your final product will just be this hemiacetal, and it won't go on further. So I guess if you want to make a hemiacetal, using the basic condition is your best bet, because you are guaranteeing that the reaction wouldn't proceed further. So yeah, your first step is your addition, and your second step is your elimination. And overall, you will have an addition elimination reaction. Of course, then finally you have another addition reaction. So you can view this this one as your addition elimination reaction, and this one as another addition reaction. Now for imine formation, it's performed under mildly acidic conditions to prevent protonating the starting amine. Remember that for this loss of carbonyl oxygen, it must be carried out under acidic conditions. However, for imine formation, the condition cannot be too acidic because this amine is actually basic. So if you have a lot of H plus just hanging around, then this lone pair can just cause this amine to act as a base rather than a nucleophile, causing it to be converted to something similar to your NH4 plus. So it's similar in structure to the ammonium ion, and you know that ammonium ions are not nucleophiles at all. So even if you replace one of these hydrogens with your alkyl group, it wouldn't make your this ion nucleophilic as well. So it must be in this. The amine must be in this form, this unprotonated form, to act as a nucleophile. So yeah, so you don't want conditions to be too acidic to prevent protonating this guy. So it can still act as a nucleophile, and then your loss of carbonyl oxygen can still occur. So here, it attacks the electrophilic carbon first, and then bond pair gets pushed up. So the bond pair ends up in an oxygen here, and then you have your NH2R group, and then you do an intramolecular proton transfer. So in this case, because it's mildly acidic, so the oxygen actually it doesn't need to grab an external proton. It can just grab one of the protons here, and then yeah, bond pair between N and H can just go back to N to give you your NHR and OH groups. Of course, you can just draw the mechanism for the oxygen grabbing an external proton, and then this nitrogen losing a proton as well. But if you want to draw the intramolecular proton transfer, then by all means, because you don't really need an external proton to proceed. However, you must make sure that the reaction conditions are mildly acidic, because if the conditions are basic, then this intramolecular proton transfer cannot occur anyway, because your strong base outside, so your external strong base can just grab one of the protons here, and then you wouldn't have a proton to protonate to your oxygen O minus group. Now, you need some external protons in this case because you want to protonate this OH group more, so it forms H2O, and that is a good leaving group. So this lone pair on nitrogen, this powerful lone pair, can come down to form a double bond, therefore kicking out this water molecule, and after that you can just deprotonate this nitrogen to give you your final product, and this is called an imine. So again, you have your tetrahedral intermediate formation, so you have your addition, and then you have your intermediate collapse to kick out H2O leaving group. So that's your elimination step. So intramolecular proton transfer and your final product. Now for enamine formation, we're using a secondary amine instead of primary. So remember just now when we were doing imine formation, we're using a primary amine. So for enamine formation, we're using a secondary amine, and there is no proton or nitrogen to lose after kicking out the leaving group. So what I mean by that is after kicking out the leaving group, you get this, and there's no proton to lose. So in that case, because we want to form a very stable product, this proton here, which is the most acidic proton in this entire molecule, it will get kicked out instead, and you will form a double bond here next to your original electrophilic carbon. So instead of having a double bond here, you have a double bond here. So remember that this hydrogen is the most acidic out of all the hydrogens. um, inside this molecule, so this hydrogen will get kicked out. This is which hydrogen is the most acidic? This question will come in very important and handy in future lectures. So be sure to really identify the most acidic hydrogens whenever you want to lose a proton. So you have your tetrahedral intermediate formation. So you have your addition reaction, and then you have your intramolecular proton transfer, and then you have your intermediate collapse to kick out H2O leading group the elimination step, and that will give you your final product after losing the most acidic proton. Now, to form a CC double bond from a CO double bond, we can make use of the Wittig reaction. So for the Wittig reaction, we have something called the elite. So how an elite is formed is first you have a halo alkane, and then you react it with PPH3. So this will give you your charged intermediate species, and then you just have to use a base. So NaH is similar to H minus, and that will help you deprotonate a proton from this CH3 group. So it becomes CH2 minus and PPH3 plus. So sometimes people also use the resonance form of this. So the resonance form is basically something so it has a double bond between C and PPH3. So this is the resonance form. So if you see this resonance form is also an elite, it's just a different representation of the elite. Now, after this elite reacts with the carbonyl group, you will have so whatever's on this end of the elite will end up at the end of the CC double bond. So the reaction mechanism is where you form a unstable four-member ring and a four-member ring collapses. So it's similar to when a tetrahedral intermediate collapses to form a good leaving group. So in this case, the good leaving group is not H2O, but this compound. So that will give you your final product. You don't really need to be very concerned about the mechanism at this stage. You just have to know that when you see an elite, replace the CO double bond with the CC double bond, and whatever's on the end of the elite will end up on the end of your CC double bond. So it's in your product is a substituted alkene. So this is the mechanism. So it's also addition, elimination. Now, there are some groups that react similarly with very similarly as your carbonyl group, and that's your CN groups. So C triple bond N and CN, because C is because your nitrogen is very electronegative, so it's similar to oxygen, and because of that, your carbon will be electrophilic. So nucleophiles can attack the carbons in these groups. So here, because the C is less electrophilic in CN than in CO, because the O is more electronegative. So the oxygen pulls the electron cloud away from carbon more strongly than N does. So the C in Cn is less electrophilic than C in CO. So some reactions are when you hydrolyze the Cn group, that will give you your carboxylate group, carboxylic acid group, sorry. So you can try to draw the reaction mechanism. It's pretty similar to the hydrolysis of esters. So you can just use this. Remember to protonate the M and that will help you form a good leaving group. So for the C double bond N group, you can also have a reduction reaction. So your your NABH4, it's a nucleophile and reducing agent. It can reduce your CN double bond to your CN single bond. So yeah, so that's pretty similar to when using NABH4 to reduce a ketone. I'll also cover some reactions that you might encounter in your competitions. So the first one is the formation of a hydrazone. So here you are just using the lone pair on N to do a nucleophilic acyl reaction. So you are doing addition and then elimination with the loss of carbonyl oxygen. So that's pretty similar to your imine formation, and the mechanism is pretty similar also. So this part is basically becomes your R group. Then for the oxim reaction, you are also using this lone pair on N to attack this carbonyl carbon. Then for this, the 2,4-DNPH test for ketones and aldehydes, because this is only reactive towards ketones, aldehydes in a lab condition, because you usually don't really, yeah, so because you want to react with a ketone or aldehyde to cause the loss of carbonyl oxygen, so this one will actually attack here electrophilic carbon. So yeah, so that will cause you to form this compound, which is bright orange. And because of that, when you have a ketone or aldehyde present, you will see an orange precipitate forming after you have added this. So yeah, that's a test for the presence of ketones and aldehydes. So why doesn't this test work for carboxylic acids or amides? Well, firstly, because when you have a carboxylic acid, you have a very acidic proton that can protonate this nitrogen. So that would just cause you to form a salt instead of your final product. So then for amides, because amides are really, really unreactive and carboxylic acids are really unreactive as well, it's highly possible that the reaction just don't proceed at all, because for amides have really, really extensive delocalization, and that carbon is not very electrophilic, so it might not want to react with this nucleophile. Now, I will also cover some redox reactions. So this is a one-pot reaction that's called reductive amination. So first, you will have this attacking here. So first you will get in something like this. And then this is in a reducing agent. So it will just remove this double bond and convert it to a single bond. So it also proceeds by the mechanism of a nucleophilic addition. So it's basically a nucleophilic addition of the H minus ion, but you don't have the H minus ion because remember what I said in the last video, H minus ions are too reactive and will prefer to act as bases rather than nucleophiles. So this is basically a controlled source of the H minus ion, and that will give you your final products. This is a one-pot reaction because your NaBH3CN is weaker than your NaBH4, and that makes it really controllable. So it wouldn't just destroy your starting ketone, and because of that, also it works in under a mildly acidic pH. So it wouldn't get destroyed by a mildly acidic pH. So this whole reaction, like all the reagents are compatible, and because of that, you can carry out the entire reaction in the same let's say same round bottom flask. So yeah, it's a convenient reaction. So the mechanism is basically all are basically carbonyl additions and sometimes eliminations. And yes, we use NaBH3CN because it's weaker and more controllable. Then for these two reduction reactions, yeah, it's pretty straightforward. So you have your ester to your alcohol, and you have your amide to your amine. So now for the summary. You can pause the video, screenshot this, and try before resuming the video to check your answers. And sometimes the question will ask you to suggest reagents based on reactions and products, and you should be able to do that too, instead of just seeing the reagents and then giving the products. So I'll be flashing my answer on screen in 3, 2, 1. So we have covered all these reactions in the previous video and this video, so make sure to remember each of them. Okay, now to the second page, I'll be flashing my answers in 3, 2, 1. Okay. You can pause the video to check your answer or try filling up the summary yourself. Okay, these are the questions and exercises, and you can try them and comment your answers down below, or you can email me for me to check your answers. So thanks so much for watching, and I encourage you to check out all the textbooks and these resources, especially this one, what makes a good nucleophile, because I feel in my first video I didn't explain it that well. So I think this article covers it more clearly, and you can certainly check it out. Also, you can look at this article for some typical addition reactions. Some are not covered here, and I think it will be very good exposure to check those out. And for this Clayton book here, I really encourage you to have a copy of it, whether digital or physical, as it's a really, really good book that covers a lot of reactions very conceptually, a lot of reactions that I won't have time to cover in this lecture series. And I think it will really help you understand organic reactions better. For me, I didn't really understand it that well until I read these books. And if you're interested, I can also share. You can message me or comment down below, and I can share how you can approach these books. What are the certainly necessary chapters you have to read, and what are some chapters that you can just read for exposure. So yeah, that's it for this video. Thank you so much for watching, and I'll see you in the next one.